Okay. A plea for somebody to be a physics lab TA on Monday afternoons from 2:30 to 5:30. Next Monday is the second lab. And,
I already volunteered.
did you? Oh. Well, please, if you are willing and able, I love to give students in the class the experience because it's going to reiterate the things you've learned, and halfway through the semester you'll start doing the labs from this semester, which helps you remember stuff for the final exam. But if I hear from nobody by this afternoon, I will very quickly start looking through old students, and because I got to get somebody. Okay, Sally's the only one I don't see here. So today we're talking about electric potential. I'm a little behind because the textbook didn't have the Gauss's law. I made that tutorial to help you see how to solve Gauss's law problems. The homework problems, we did 3 and 4 were the two that I did with Sade this morning. And after you understand how Gauss's law works, they're startlingly simple. But the key is understanding how Gauss's law works. Once you understand, they're simple. But if you don't understand Gauss's law, well, that's why they're there, to make sure you understand. So if you're having problems with those, feel free to contact me for help. Moving into electric potential. We're going to start where we ended up the last 3 slides from last lecture, the first 3 slides here. So we went through, thank you. Yeah. Take Cassie's away too. She's also not following the rules. Okay. I went through this here with the parallel plates to very quickly show how we find the electric field between the plates. Now, one thing I said that I should have clarified. I said it doesn't matter if the second plate is there or not. Everybody remember that from Wednesday? It does matter in this sense. If I didn't have the plate on the right, where would the charge on the left plate be situated? It would be on both sides of the surface. But because of the charge on the right, because of the positive plate here, it's pulling the negative charge, so it turns out that all of the negative charge is on just the inside surface and there's none on the outside surface. So that doubles how much charge I have in my little Gaussian surface. And how does the electric field relate to the charge enclosed? It's what? Okay, well the correct answer was, by Gauss's law, the flux is equal to the charge enclosed divided by epsilon 0. And the flux is electric field times area for my little Gaussian surface. So the electric field is just proportional to the charge enclosed. So if I have only half as much, if I didn't have the second plate, I'd only have as much charge enclosed, I would only have half the strength of the electric field. So that was the one aspect that changed. Without 2 plates, the charge would be on both sides. I'd have some minus charge here and some minus charge here. But with the second plate, it pulls it over so all of the charge is on the inside. I just had to correct that. I noticed in my tutorial video, I made a comment there on YouTube. I actually accidentally said, now I'm going to work a problem in cylindrical symmetry. Don't know where my brain was. It was spherical symmetry. That was a misstatement, I think, one time, but I was very, very appalled, and yet my video editing skills are nil, so I didn't go change it. I just accepted it. Just like my wife calling. My phone was on silent, just like yours should be. But my computer wasn't on silent. And those of you who are in the Apple world know that your Your computer rings and you can talk on your computer when somebody calls you on your iPhone. Right? Everyone with Macs and iPhones. It's actually really convenient, especially if you lose your phone. Okay, so given that we have an electric field and force and electric field are related by the relationship that force is equal to charge multiplied by electric field, then using Newton's second law, we know that charged particle, if I put a charged particle in an electric field, it's going to be accelerated. And if it's accelerated, its kinetic energy is going to change, right? This is going to have a different speed. So there's going to be work done and a change in energy. And so what we're going to focus on today is looking at the energy for charge as it relates to other charges or electric fields. So this picture here, which I think is the very last one we had last class period, is illustrating once again the parallel between gravitational force and electrostatic force. Now when I say electrostatic, I mean the electric force on stationary charges. Now we're going to talk about charges moving in just a moment. Still consider the field of electrostatics though. Okay, so if I have a gravitational situation, I have something like the Earth has a lot of mass. Remember, mass is the gravitational charge. So the Earth has a lot of mass, it has a lot of gravitational charge. If I put something else that also has mass, gravitational charge, there's going to be a force between the two. And how is that force directed? It's always attracted. Always pull them down. So if I have a piece of mass up here, let me not drop my stylus. Let me drop this little flower instead. If I have this mass up here and I let go, because of that force, how does it respond? It falls, it accelerates downward, and what happens to its kinetic energy as it falls? The kinetic energy increases. What about potential energy? Decreases. Okay, so boom, it all happened just like we said. Potential energy, review your energy things. The potential energy was determined based on the work done by a conservative force. Conservative forces are the forces that will store energy and give it back without eating any of it. A simple way to determine if a force is conservative is if the path matters. If the path matters, it's not conservative. If the path doesn't matter, it is. So electric force is just like gravitational force, which means it's also a conservative force. So we can define a potential energy. If I have a negatively charged Earth, what kind of mass, not mass charge now, but electric charge, do I need to have for it to be attracted? Positive, because with charge, opposites attract. Notice we already have a difference now. Before, there was no positive or negative mass, there was just mass. But now if the Earth is negative, then a positive charge is going to behave like it would have been for having a mass there. But if I have that positive charge, it has a force. Because it has a force, there's going to be an acceleration. There's going to be work done. And as it falls, it's going to gain kinetic energy. So what's going to happen to its potential energy? It's going to have to decrease. Because energy can't be created or destroyed, energy itself is conserved. So you're just going to convert from electrostatic potential energy to kinetic energy. Now before I move on, let's consider what's not in this picture. What if the Earth had a negative charge and I had an electron up here? So all I did was change it from like a proton to an electron. When I let go, what's going to happen? It's going to go up instead of down. Go on, leave your water over there. All right, okay, put it in your bag. I will eventually be a rule enforcer. So the electron would do the opposite thing that a proton does. As it flies away, what's happening to its kinetic energy? Well, kinetic energy doesn't have direction. It's increasing. So if its kinetic energy is increasing, what's happening to its potential energy? Decreasing. And that's a basic rule for physics. Things will naturally go to the lowest available potential energy state. So for a negatively charged Earth, a proton falls down because that's lower potential energy. But an electron falls away because that's also a lower potential energy. They're both falling to lower potential energy. Which is, I think, the clicker question. What direction does the charge move? Now, I should have used the word potential. Everything here should have been, well, everything in those two, potential energy. Okay, everybody answered. Only one person had the wrong answer. This is, of course, what I said approximately 30 seconds ago. That it's a rule in nature that things naturally go to a lower potential energy. You let them go, they go to a lower potential energy. Now, we haven't talked about voltage yet, so that would have been your hot tip. It's not about voltage yet. We haven't talked about it. We'll have a question about it coming up. Okay, this here, I have to switch the input so you can see it. It's a cool little, come on, there we go. It's a cool little simulation about charge. Now, what this allows me to do is right now I have minus 1 millicoulomb. So I'm going to put a negative charge, and I'm going to put it right there. There's my negative charge. All of those little arrows are showing the electric field that's created by that charge. So right now the negative charge has electric fields that's coming into it from all directions. Matches what we've learned, right? It's symmetric. If you go around a circle, the radius is all that matters for how strong the electric field is. It's always pointing toward the center. Now, I am going to I'm going to now add a test charge, and I'm going to put a positive test charge here. So I'm going to put a positive test charge here. So if I put a positive test charge here, what's going to happen when I let it go? It falls to the center. It's exactly what I was describing. Now we can do things a little more complex. Like let's put a fixed positive charge here. Now we have the electric field due to the two charges. It's adding up the electric field vectors at all locations based on the two charges. And if I put a test charge, let's say I put that test charge right here. Now that's a negative test or a positive test charge. So in terms of the electric field, what direction is the force on a positive test charge? Same direction as the electric field. So what direction will the force be when I release it right there? It's going to be away. What is this charge going to do? Is it going to crash into either of the charges? Okay? I heard people say yes. Of course, this is a simulation because I can't really do this myself, but let's click and see. No, it did not. Why not? The arrows tell me the direction of what? The electric field, and thus for the particle it's going to be the direction of the force in the particle. So it's going to tell me the direction the particle accelerates. So when I released it, it was accelerated that direction. As it moved, like when it got to here, the acceleration was almost tangential, so it's making it curve. But because it had a pretty large charge comparatively, I mean, there's no masses here, so we can't really do a comparison. But with a reasonably large charge, it didn't deviate very much. It just went flying off. So let me lower the charge. Now it's 1/10 the charge. Let's see what happens. Still escaped. Unfortunately, oh yeah, I can go smaller. 1/100th the charge. It moves very slowly. We're at the fastest time setting. Yep. Still gets lost. Okay, so changing the charge didn't matter. Is there a place I could drop it where it doesn't get lost? Oh, my goodness. It's just never going to move there. Reset. Kind of cool, huh? See what would happen if I started it here. I'm gone. Now those charges, it's not perfect. Those charges aren't interacting with each other. They're only interacting with the two fixed ones. So this has some interesting presets. This is the one that we just did essentially. Okay, so that's not a big deal. Let's choose here they're going in between, oscillating back and forth. Sally?
So you said that it shows us the direction of the acceleration?
The arrows show us the direction of the electric field, which tells us the direction of the force. If it's a positive charge, it's going to be parallel to the electric field. If it's a negative charge, it's opposite. And then using Newton's second law, the acceleration is in this direction of the net force, so that's also the direction of the acceleration. Okay, now the last one, which is the one that's most interesting to watch. Here we have essentially a positive cage. You see the electric fields outside of the cage are pointing out. The electric fields inside the cage are weak, but pointing in. Oh, it got out. Let's just put another one in here. Okay, putting it on the axis, no fun. Putting it up here, no fun. Putting it here, and we get fun. It's kind of fun to see how these things play out, but they're all just using what we've learned. Yes, Cassie?
So what are some things that take advantage of, like, the oscillating movement, like, things that have been made, like, created devices?
That take advantage of the oscillation?
Yeah, like, you know, bouncing it back and forth.
Have you ever used a mass spectrometer?
Yeah.
There are different kinds of mass spectrometers, and one of the more advanced types is called the quadrupole mass spectrometer. And the quadrupole mass spectrometer, it actually makes a, I'm trying to remember if it's electric field or magnetic field. Either one would work in some regards. But I think it makes magnetic fields, but it makes quadrupoles, so you have two norths, two souths. And then it oscillates, and the oscillation depends on the charge to mass ratio. And if you have exactly the right charge to mass ratio, it stays oscillating in a stable pattern and makes it through. If it doesn't have that stable pattern, then it gets thrown off, and so you select only one charge to mass ratio. How do I know? Because in my research I had to use these. And I decided it was far too complicated. Okay. How does all of this come to numbers and equations? Potential energy we learned is defined. Remember those three instead of 2 for the equal sign means it's defined as. So the change in potential energy is defined as the work done by a field. So we did it, the work done by, well, it's not only by a field, but in this case we're talking about electric field, so it is. We did it for the gravitational field, now we're going to do it for the electric field. As you can see, those there are calculus steps. If you have a constant electric field, you can do this without calculus. But if it's changing, you can't. So that's why I showed the calculus in there, because for things like a point charge, you have to use calculus. For things like this, you don't need to use calculus. For this, I can just say the electric field parallel to delta x multiplied by the charge, and that minus sign because of this. I'm going to take away that last thing because it makes it look too busy. So if we have a constant electric field, the change in potential energy is minus the charge we put in there times the electric field parallel to the distance the charge moves times the distance it moves. Simple practical examples. If I put a positive charge here, and let's say I'm holding it, and I move the charge up here, how much work is required to make it do that? And let's just go with simple things. Positive, 0, negative. You're right. 0. Why 0? Right, because my delta x was perpendicular to the force. So there's no work to move a charge perpendicular to the electric field lines. Now, that being a positive charge, if the charge moves to the right, then I'm moving parallel to the electric field, and my work would just be the electric field strength multiplied by my charge, multiplied by the distance, and then, of course, I have to throw in the minus sign. So if I let the charge go here, it's going to always go to low potential energy. That minus sign is what tells us, oh, that was lower potential energy. Yes, ma'am?
How is the delta x defined? Is that defined? Like, do we...
Delta x is...
Which is positive movement and which is negative?
Yeah, delta x is the final position minus the initial position.
Okay.
And so if you start here and end here, your delta x would be going like that.
Yeah, but how do we pick which way would be positive or negative?
Well, it's starting point to end. Right. This is my x final.
Yes.
And this is my x initial.
Yes, I get that.
Okay. So then I'm not sure what the question is.
So
I
my
thought that
question
was
is,
it.
like, do we automatically say that, oh, starting at the positive is, if we impose, like, for example, a coordinate system, do we say that, like, this side is 0 and then that makes going this direction be, like, an increase in basically the x value versus...
Well,
yeah.
in this case, I basically take my electric field direction, because I put electric field parallel, and I say that direction is going to be my positive direction.
Okay.
Okay. That was the question?
Yes.
Okay. I was confused about it. It's from start to end. Yeah. So a positive charge will move away from the positive charge and toward the negative, just like we've learned. That means it's going parallel to the electric field lines. The negative charge, if it starts here, it has a force that's opposite the electric field because of negative charge. And so it goes the opposite direction. Nice straight line there. And so because my electric field is to the right and my delta x is to the left, then that would be a negative electric field times delta x, right? But the Q is also negative, and I have a negative sign out here, so I'd have 3 negative signs. Negative, a negative field times a negative distance, which means a negative change in potential energy. It's also going to go down in potential energy. So now we're going to go to looking at a point charge that's causing the electric field instead of parallel plates. With the parallel plates, it was simple. We didn't need calculus. The work was just the electric field parallel times the distance it travels times the charge, and then the minus sign because change in potential energy is defined as minus the work. Right, so that was simple if we had a constant electric field. But if you have a point charge, then we have the electric field strength is equal to KQ over R squared. And so the electric field is going to change if it moves to higher, or, as it moves in response to that force. And so we had the gravitational field was GM over R squared. And from that, does anybody remember what the equation for the gravitational potential energy was? Nope. It was minus capital G M1 M2 over R squared. So following that example, what do you suppose the electric field potential energy equation is going to be? Oh, I made a mistake. That's over R. Yeah, I didn't notice there, but I noticed when I get to the one that I'm trying to do. I make that mistake way too often because force and potential energy, basically the difference is over R versus over R squared. The potential energy is over R for point charges. The force between point charges is over R squared. Now, we will see here how calculus allows us to get that equation. So force, electric field times Q, is KQ1 Q2 over R squared. So if I take that and I integrate F dot dr, you can't multiply by R because you're not moving from the from zero separation out to some point. You're moving from this distance to this distance. So you're not just multiplying by R. You do the integral and you find that your change in potential energy is KQ1 Q2 over R final minus KQ1 Q2 over R initial, which gives us U as KQ1 Q2 over R, which is all good except for one thing. That one thing is, I think I made a sign mistake. Yeah, because I should have had, I believe, a minus sign there. Yeah, I am. Actually, no, maybe I was wrong with the sign before. Now, I should have thought about the sign before. I am pretty sure that I was wrong in putting that minus sign there. Because of having two charge types versus one charge type, it becomes a little different. So we have this equation for the potential energy. KQ1, Q2 over R, not over R squared. The potential energy, then, we define zero potential energy as the potential energy when they're infinitely far away. 1 over R, if R is infinity, what does that approach? As R approaches infinity, that approaches 0. So we have potential energy approaches 0 as they approach very far apart. If I have two positive charges, these signs are right. I had to sit here and think about it. Right in front of you, you saw me thinking. It's a rarity, right? Our teacher never thinks. If I take these two positive charges and I bring them closer together, what's going to happen to the potential energy? It's going to increase. I could give you reasons why all over the place. For one, they're positive charges. They don't want to come together, right? So I have to pull them together. I have to put work on it. If I put work in, what happens to potential energy? It has to increase, right? We learned that in thermodynamics. We learned it, and we learned it everywhere. So if I force these together, potential energy increases. If I let go, what are they going to do? Go back apart, converting that potential energy back into kinetic energy. Conversely, if I take two negative charges, I have them out here and I let go, not two negative charges, a positive and a negative. The positive and the negative are going to be attracted and come together. Now here's something that, quite honestly, I never thought about when I was taking physics class or chemistry class. We talk about the energy of, let's say, an electron in the hydrogen atom. Everybody familiar with that? What owns the energy? What particle do we assign it to? I would have always said we assign it to the electron. In fact, we say the electron's energy. But that's not right. It's the energy between the electron and the nucleus if it's a hydrogen atom. Hydrogen atom being the only atom we can solve completely. If it's anything else, well, actually any atom that's had all but one electron ripped away, we can solve it completely. If it has 2 electrons, well, we can give you a good approximation. 3 electrons, you know. Okay, but if you have the nucleus and 1 electron, the energy is the energy between the nucleus and that electron. If you have something like a helium atom with a nucleus and 2 electrons, a neutral helium atom, then how is the energy identified? What does it belong to?
Between the 3?
Yeah, it's really between the 3. We generally will say, well, one is between this electron and this nucleus, and the other one is between this electron and the nucleus, but they affect each other. And so it's an energy spread between all 3. And one of the cool things, if you've ever studied helium, if you have a helium atom with both electrons in the n equals 2 state, if one falls from n equals 2 to n equals 1, what happens? It auto-ionizes. The energy goes to the other electron, and it has enough energy to break free. We'll study that part of physics later. This is important when you talk about chemistry. This is very fundamental to chemistry, because chemistry is, even in the quantum understanding of the atom, we're still essentially starting doing the same calculation that we do for the moon orbiting the Earth. Do you guys remember doing that first semester? A few people say yes. You have a force between the Earth and the moon, a gravitational force. It's an attractive force. And you have the moon moving. And then we calculate what the total energy is between kinetic energy and potential energy, and we use Newton's second law with centripetal force, and we can solve to find, the total energy of the moon. And the gravitational force between the Earth and the moon produces a negative potential energy, and the kinetic energy is positive. If the total energy of the moon-Earth system is less than 0, then the moon's bound to the Earth. It cannot leave. But if the moon moves fast enough, if the total energy is greater than 0, then the moon says bye-bye. The moon is released. And that's the same thing that goes on with atomic orbitals. You have the electron out here that has a potential energy. In this case, we do the it has to be more complicated, electromagnetic, potential energy between the electron and the nucleus. At first step, we just said the electrostatic energy. And that's a negative energy, and it's going to become more and more negative as it gets closer. It goes to 0 if it gets infinitely far away. And we have its kinetic energy. And if that total energy adds up to something that's negative, the electron is bound, it stays with the atom. But if you give it enough energy so that the total energy reaches 0, then it's free to go. So you're probably used to saying, well, the ground state electron energy is minus 13.6 electron volts for a hydrogen atom. That's the lowest energy state it can have. If you add 13.6 electron volts, it'll get up to 0. And then the electron has 0 energy, it's free to go. And so we call that the ionization energy. Yes?
So how does that work as far as breaking the bonds between 2 different atoms?
It's basically the same thing. Whether you're talking atomic or molecular orbitals, you still have a negative energy. And as long as you have negative energy, it's bound. And if you add enough energy to make it 0 or above, then you can ionize it. So for instance, we talk about the safety of cell phones. Cell phones put out electromagnetic waves. Those electromagnetic waves can be absorbed by the electron's bond to an atom. The energy of the microwaves we use in our cell phones is small enough that if it is absorbed, and of course it can only be absorbed if it goes between one state and another state. But if it's absorbed, it's still going to be bound. It's not close to enough to free the electron. Whereas if you get up to ultraviolet radiation, you can have enough energy in the radiation that when it's absorbed, the electrons will have positive energy and be free. And that's when it's dangerous. So that's what we call ionizing radiation. So microwaves are not ionizing radiation. We generally consider them safe. Except for you don't want to put your head in the microwave oven. Why? Because it does transfer energy. You absorb some energy. And that energy, we learn in thermodynamics, makes things move faster. And what do we call it when things move faster? It's hotter. And so you can cook yourself with microwaves, but you can't break the bonds. And so that's where a danger would be with microwaves. You have enough microwave radiation, you can actually cook things. Yeah.
Okay, I might be off on the concept, but like...
I'm already well off concept, so let's go.
Okay. So you know like the fans that are ionizing, they pull the air through?
Mm-hmm.
Can that be a negative effect if there's something that, like microwaves or something being pulled through there?
I don't think so. I mean, smoke detectors ionize too, right? Smoke detectors have little radioactive americium in there to ionize particles, and then it puts two plates here, one positive, one negative. If I have an ion between them, if I have a net charge that's not zero, and I have it between the two plates, one's a positive charge, one's a negative charge, well, the ion's going to get pulled over to one side or the other. And the smoke detector, when that happens, it says, "Oh, we got it. We got a hit, got a spike." And it's measuring how many of those occur per second. You take away the americium, you take away the ionizing radiation, it doesn't measure anything. But we don't worry about that. Now, you're not supposed to throw away your smoke detector because you're throwing away a radioactive sample. Just in case you've done that recently.
No, I haven't.
Okay. What you should do is take it apart and take that little americium sample because it's actually reasonably radioactive. Good to know, right? Americium being named after the United States of America. Did you say Earth? I said America. Oh. Amerigo. Wow, it's been a long time since I was in grade school. Can't remember his name now. Electric potential energy can be both positive or negative. So these are some graphs. The one on the left is showing gravitational potential energy. Gravitational potential energy is always negative. Approaching zero when things get infinitely far away. If I have two charges that are opposite, a positive and negative charge, then I have the same thing for electric potential energy. But if the charges are the same side, both positive or both negative, it's the reverse of that. And so the fact that we have two different options for electric potential means that we're going to have some differences. Okay, problem. I'm going to take the time to work through the problem, even though I'm clearly going slowly today. A simple problem to help us think about this energy thing. So we have a simplified form of the storm cloud. Remember in lab we had the students up here talking about how lightning occurs. This is a simplified model just saying we have a charge separation. We have 50 coulombs on top and only minus 20 coulombs on bottom. Where'd the other charge go? Not my concern. They're separated by 8 coulombs. And then our question is, I put the question picture again. What is the electric potential energy of the pair of point charges, assuming that potential energy is zero when they're infinitely far away? How do you find that? U is equal to, what's my equation? only over r. Remember, I made that mistake too of saying r squared, because the force is over r squared. Actually, it's positive. I made that mistake earlier. I'm making all the mistakes for you. So, yes. And it's putting in our numbers. That times 50 coulombs times minus 20 coulombs, all divided by 8,000 meters. Okay, 50 times 20 is 1,000. We have the minus sign. So I'm going to have 1,000 divided by 8,000 is 1 over 8. So I basically have equals minus 8.988 times 10 to the 9 newtons meters squared. Uh-oh, don't have space for my meters squared. And that's really kind of important to have the units right. Notice the coulomb squared already canceled. Divided by 8 meters. Cancel one of those meters. I'm going to have units of Newton meters. What do we more likely use instead of Newton meters? Newton meter is a joule. So it's going to be joules. And of course, I really want to say 1.111, but of course that's not exactly right. It's like 1.123.
Yes. 5.
We'll just put 1.12 times 10 to the 9th joules. That's a big amount of energy, right? 10 to the 9th, 1.12 gigawatts. Great Scott. And of course, you guys know, I said this, right? It's not pronounced gigawatts, it's pronounced gigawatts. But they had no one, they've admitted this, they had no one on the entire set that knew how to pronounce GIGA. And so they just guessed, and they guessed wrong. You see that all the time. It's especially disappointing when it's a show like Scorpions, where they're supposed to be super geniuses, and yet they don't know basic science words. You know.
That was Scorpion. That was off Scorpion.
Not that, but there was just last week's episode, or this week's episode, I guess it was. You know, they just mispronounce a very common scientific word. I'm like, really? Okay, moving on. I forgot one thing. What did I forget? The minus sign. I said it up here and didn't write it. And of course, once I didn't write it, I didn't put it here. What does it mean that it's a negative energy?
Attractive.
Yeah, it means it's attractive. Okay, so we are not going to have to do any work to make them come together, but we have to do work to make them go work. I've got 8 minutes left. We're doing good. If I have more than 2 charges, the potential energy calculation is the potential energy between each possible pair of charges. The way we can think about this is you say, okay, let me put one charge here. It takes no energy to put the one charge there because it's not interacting with anything. Then I'll take a second charge and bring it from infinity to its position. Then I'll take third charge and bring it from infinity to its position. And so I can calculate the work that's necessary for each one of those, and I get those 3 terms, one for bringing the first one in, and then the next 2 for bringing the second one in with the 2 charges there. And what does this energy belong to? The entire assembly. We don't say, oh, this charge has this much potential energy, and this one has this much, and this one has this much. And we don't split it up 3 ways either. We just say the assemblage has that much potential energy. Okay, this will probably finish our time. We'll see. What is an advantage of using energy instead of using force? something that makes it simpler to use energy instead of force. Remember last semester, I said a lot of problems we can solve them using force methods, Newton's second law, and the kinematic equations, or we can solve them with work energy. What was that made the work energy simpler? Well, that was a requirement for using that, but not what made it simpler.
You don't have to know where the position is or the velocity is?
Okay, we don't have to know the velocity or acceleration. We need to know the speed, right? It's scalar instead of vectors. It's a lot easier to work with scalars. I can add two scalars. 5 plus 7 is 12. But if they're vectors, 5 this direction and 7 that direction, it depends on what the directions are, and it becomes a much harder problem. So we prefer to do our problems using scalars, so energy is the method we like to work our electric problems when we can. So here the problem is find the electric potential energy for the array of charges here. What is my method going to be? Find it for each possible pair and add them up. So my potential energy is equal to KQ1, Q2 over R12 plus KQ1, Q3 over R13 plus KQ2, Q3 over R23. And so then I just have to put in my numbers. R13 is very simple, right? Q1 is at 0, 0, and Q3 is at 3, 0. So R13 is just equal to 3 meters. Likewise, R23 is very simple. That's 4 meters, which makes R12 simple. Everybody heard of a 3, 4, 5 right triangle? Yeah. This is a 3, 4, 5 right triangle. 3 squared plus 4 squared, that's 9 plus 16 is 25, which is 5 squared. So that's a 3, 4, 5 right triangle. So there I have my distances, and then I just have to put the charges in. I'm going to just factor out the K and do everything else. And then I just put those together. Obviously, get a common denominator, which in this case would be 60, I believe. And go from there. So we don't need to finish the calculation. I think we could all manage the math. See the method? Now, on the test, I will be giving you the equation that says U is equal to K Q1 Q2 over R. I won't give you the equation that I wrote here. Why not? Yeah, you need to know, the potential energy is the potential energy between each possible pair, and go from there to there. Right? Because you have the equation for the potential energy. You have to know how to use it. I point that out because I've given a problem like this in the past, and students are all, I didn't know what to do with multiple charges. Well, you need to know. Okay, electric potential. Electric potential, we never talk about the gravitational potential. We talk about the gravitational field. We talk about the gravitational potential energy. The electric potential is the electric potential energy divided by charge. So electric potential is defined as actually this way. The change in electric potential, we use the symbol V for electric potential, is equal to the change in electric potential energy per unit charge, per charge Q, excuse me. That's how we define electric potential, defined by the change. What are the units? Well, what are the units of potential energy? Joules. What are the units of charge? Coulombs. So the unit is a joule per coulomb, which we call a volt. Named after Alessandro Volta. Because the units are volts, we have gotten really lazy and we call the electric potential the voltage. So we're far more likely to hear somebody say, what's the voltage of that battery, than to say, what's the electric potential of that cell? Because usually you're talking about a cell when you say battery as well. So the voltage, the electric potential, is a measurement of the potential energy per charge. So high voltage means that each charge, each electron, has a high potential energy. Low voltage means the electrons have low potential energy. And potential energy is always measured with respect to a reference. So the same thing is true of voltage, of electric potential. You always have to have a reference and you're measuring the electric potential difference between two places. Okay, I am out of time. I should have put that cool little picture. I'm going to make a positive post. And it's a picture of a battery with the positive post in the battery. Goes well right here. Okay, have a great weekend. Enjoy the next to last weekend of meaningful football for the season. So for Monday, do the concept coach questions that were written for today on the schedule.